Unit vectors. Welcome, everyone. Today we are going to dive into a very important concept in vector algebra, unit vectors. Now, as you know, when we work with vectors, we usually care about two things: how long the vector is and which way it is pointing. However, in many mathematical and physical problems, the actual length or magnitude of the vector isn't actually the most important part. What really matters is simply the direction the vector is pointing. To handle these specific situations, we use a special tool called a unit vector. So, what exactly is it? By definition, a unit vector is a vector that has a magnitude of exactly 1 unit. Think of it this way: its primary purpose is to act as a pure indicator of direction in space. Because its magnitude is exactly 1, it allows us to specify a direction without adding any extra weight or scale to our measurements. It's like a pure pointer. In the next slide, we will look at the mathematical way we actually construct this vector from a standard vector. Understanding unit vectors. Now that we've established that a unit vector is simply a vector with a magnitude of exactly 1, let's dive deeper into how we actually understand and create one. First, let's look at the concept. Suppose we are working with a non-null vector, which we'll call a vector. Now, non-null just means it's not a zero vector. It actually has some length and direction. Our goal is to find a special version of this vector, which we call a cap, that is, with a little hat on top. This a cap must point in the exact same direction as our original a vector. So, how do we strip away the extra length while keeping that direction perfectly intact? The trick is to divide the original vector by its own magnitude. Think of it as scaling the vector down until its length is exactly 1. If we look at the math, we can express this in two ways. First, we can write it as a cap equals 1 divided by the magnitude of a vector, multiplied by a vector. Or, even more simply, you can think of it as a vector divided by the magnitude of a vector. Both notations mean the same thing. We are using the magnitude as a scaling factor. To make sure we're all on the same page with the notation, a vector represents our starting vector. The vertical bars around a vector represent its magnitude or its total length, and a cap represents our final resulting unit vector. In the next slide, I'll show you a clear, step-by-step process you can use to perform this calculation every single time. Finding a unit vector. Now that we understand the theory and the formula behind unit vectors from the previous slide, let's break this down into a practical, step-by-step process. If you're ever stuck on a problem, you can always follow these 4 manageable steps to find a unit vector in the direction of any given vector. Step 1. Calculate the magnitude. Before we can scale the vector down, we need to know its current length. You'll do this by finding the magnitude of vector, which we denote as the magnitude of a. To do this, use the formula, the square root of x squared plus y squared plus z squared. This works perfectly for vectors in 3-dimensional space. Step 2. Find the reciprocal. Once you have that magnitude, you need to find its reciprocal. In other words, you are calculating 1 divided by the magnitude of a. This value is what we will use to scale our vector. Step 3. Scalar multiplication. Now, take your original vector, and multiply it by that scalar value we just found, which is 1 divided by the magnitude of a. This is the core step, where we actually shrink the vector's length without changing its direction. And finally, step 4. Simplify. To finish the problem, simply distribute that scalar value across all the individual components of your vector. Once you've distributed the value, you'll be left with your final unit vector. In the next slide, I'll show you a real-world analogy to help you visualize why this process of maintaining direction while changing magnitude is so important. And then we will walk through a concrete numerical example together. Real-world analogy. Now, before we dive into the formal calculations and the worked example in the next slide, let's take a moment to step away from the math and look at a real-world analogy to help this concept really click. Imagine you are out hiking and you are using a compass to navigate. When you look down, the compass needle is pointing north. Now, think about your journey. Whether you decide to walk 1 kilometer north or you trek a massive 100 kilometers north, notice that the direction itself, that heading of north, has not changed. The direction is constant. In this analogy, the concept of north acts exactly like a unit vector. It provides the pure direction without any extra scale. The distance you travel, whether it is 1 kilometer or 100 kilometers, acts as the scalar magnitude. Just like we discussed in the previous slides, if you take that direction, our unit vector, and multiply it by your distance, our scalar, you determine your final position in space. This perfectly illustrates how a unit vector provides the where in terms of direction, while the magnitude provides the how far. Worked example. Our problem is to find the unit vector, which we denote as a cap. That points in the same direction as the given vector, where O equals 3i hat plus 4j hat. Let's start with step 1, which is to calculate the magnitude of vector, To do this, we use the magnitude formula we discussed earlier. We take the square root of 3 squared plus 4 squared. When we square those components, we get 9 plus 16, which simplifies to the square root of 25. Taking the square root, we find that the magnitude of A is exactly 5. Moving on to step 2, we now apply the unit vector formula that we saw on the previous slide. We take 1 divided by the magnitude of A and multiply it by the original vector, A. Since we just found the magnitude is 5, our equation becomes 1/5, multiplied by the quantity 3i hat plus 4j hat. In step 3, we simply simplify the expression by distributing that 1/5 across both components. This gives us our final result. The unit vector a cap equals 3/5 I hat plus 4/5 j hat. Now, as a good mathematician, you should always verify your result. To ensure this is truly a unit vector, let's check its magnitude. We take the square root of the quantity 3/5 squared plus the quantity 4/5 squared. Squaring the fractions gives us 9 over 25 plus 16 over 25. Adding those together, we get 25 over 25, and the square root of 1 is simply 1. Since the magnitude is exactly 1, we have confirmed that a cap is indeed a unit vector. Now that we have covered the theory and the step-by-step process, let's put everything we've learned into practice with a worked example. Before we move on to some common pitfalls to watch out for, let's take a moment to reflect on how this calculation perfectly follows the steps we outlined earlier. Common mistakes to avoid. Now, before we wrap up our lesson with the final summary, I want to pause and discuss some common pitfalls. Even if you understand the formula we used in our worked example, it is very easy to make small errors that lead to the wrong answer. Let's look at 3 specific mistakes to avoid. First, there is the mistake of forgetting the magnitude. I often see students who, after seeing a vector, simply change the notation to a cap without actually performing the division by the magnitude. Please remember, the cap symbol is not just a decorative label. It represents the result of a specific calculation. You must actually scale the vector down to a length of 1. Second, watch out for incorrect magnitude calculations. When you are finding the magnitude, remember the order of operations. You must square each component first, then add those squares together, and finally, take the square root. A very common error is performing the squaring and addition, but forgetting that final, crucial step of taking the square root. If you forget that, your vector will not have a magnitude of 1. Finally, be careful not to confuse the direction. By definition, the unit vector we are calculating must point in the exact same direction as our original vector. If you were to multiply your vector by a negative scalar instead of the positive reciprocal of the magnitude, you would end up with a unit vector pointing in the opposite direction. While it would still have a magnitude of 1, it would no longer be the vector we are looking for. Keep these points in mind, and you will be well on your way to mastering unit vectors. Now, let's move to our final slide to review the key takeaways. Key takeaways. First, remember the fundamental definition. A unit vector is simply any vector that has a magnitude or a length of exactly 1. As we discussed earlier with our compass analogy, The primary purpose of a unit vector is not to show how far you are going, but to specify direction exclusively without adding any extra scale or weight to your measurement. To find this, you must always use the formula we practiced in our worked example. To find the unit vector, which we call a cap, you take the original vector, and divide it by its own magnitude, which is written as the magnitude of a. Finally, keep in mind the most common examples you will see in your textbook, the standard basis vectors, which we call I hat, j hat, and k hat. These are all unit vectors because they point directly along the x, y, and z axes respectively, and each one has a magnitude of exactly 1. All right, we have reached the end of our lesson, so let's quickly recap the key takeaways to ensure everything is clear before you move on to your practice problems. If you have mastered these points, you are well prepared to tackle more complex vector operations. Great job today!